Hi, everyone. This is Giacomo, Alex, Will, Nick, and Jonathan, and we're presenting on an electric torque vectoring system for the BU Motorsports team.
So a little bit of motivation behind our project. So we were approached by our client, Terry Motorsports, which is a student organization here at Boston University. Basically, they specialize in designing Formula-style electric race cars, which are life-size, as you can see on the right side. An actual human being like yourself could actually fit inside and drive them. So previous models, like the one here on the picture, named Stella, these are driven usually by one power unit. But the next generation Formula cars that Terry Motorsports wants to design will have individually controlled rear-wheel electric motors. So where we come in is, in order to best utilize the performance of such independent drives, we came in to design a fail-safe torque vectoring system, in which we'll now go into more detail.
Yeah, so what is torque vectoring? So if we break it down word by word, torque. The motor generates torque that is transmitted to the wheels in some fashion or another, and that is the force you feel in your rear end when you press the gas pedal. Now, vectoring is what we can use the independent drives for. If we vary the amount of torque at each wheel, you'll feel a turning moment, which is basically just a force to one side or the other, that causes the car to want to move in one direction or the other.
So why torque vectoring? You might, if you've ever been on a train before, ever been in a car before, when you're rotating, you feel force in your rear end, and you go one side or the other side. And so you might realize that when you're going around a corner, your outside tire travels further than your inside tire. And so we reduce the power of that inside tire, which means the outside tire essentially gets more force, it travels further, and the physics of this works out that basically prevents slippage. And when the driver's handling the car, it should steer better, it should feel better, it'll be faster.
So for our system, we had 4 major contributions. We had one, we wanted to keep the system affordable compared to commercial solutions, which are often proprietary and can cost upwards to 10 times our system. Ours came out to like $500. Theirs can go to $1,000 to $10,000. We also want to keep it modular so that future teams or other teams can integrate our system into their car. In terms of implementing this modularity, we wanted to keep the system simple. So you only have to change like a couple of variables, and you just need to tune the system, and you can hopefully implement the system. We also wanted to keep it efficient, as we only manipulate the motor outputs of the car instead of manipulating the braking, which would reduce efficiency and energy consumption.
So our client, Terry Motorsport, came to us with a few requirements, starting off with the hardware and software of it. They wanted it to first be realistic. They wanted to make sure that if they gave it the length of the car, the weight of the car, that we'd be able to best tune our system to the design of their vehicle. They also wanted it to be reliable, which if it's going into a race vehicle, that's pretty important, so that the feeling is a very subjective measure, but the feeling from the driver is not impacted in any negative way, and they're able to control the car as they see fit. Very relatedly is the speed of the system. You can imagine if there's a long delay between you pressing your foot on the gas and the car actually going, that would not yield the best lap times. It would not give the driver enough confidence to perform at their peak. And finally, above all else, was safety. This is being put into a car that is much lighter than yours, has about the same amount of power, and you can hit 60 miles an hour with nothing but steel in front of you. So you want to make sure that they are in no way put in any sort of danger at the hands of our system. In terms of actually putting everything together, they have space requirements. After all, it's a very compact vehicle, and so they gave us a limitation of 8 inches on all dimensions. And unfortunately, the vehicle is supposed to go into does not exist yet. And so they wanted to have a little demonstration model so you could see the effectiveness of our system in a more tangible way as opposed to just looking at numbers scrolling on a screen. Just to give an idea of what it would kind of look like. Again, a single-seater race car, starting with the components of the car the driver interacts with. That would be a sensor in the steering wheel and a sensor in the throttle pedal. These signals get fed into what we've tokenized as the auxiliary controller. We'll go into more detail as to why we necessitated that. That communicates over a single set of cables to our main controller, which does all the magic torque vectoring. And finally, that interacts with the electronics of the car itself. Those are provided by the club. They are chosen by the club, and we are just giving them essentially 2 throttle signals for them to do whatever they please with.
So a little bit more in detail about the system design. So we'll start here with the how the data is collected. So you have on the left here 3 sensors: the throttle, which measures the power applied to the vehicle, so you step on the foot pedal. The second one's steering, which is the amount of angular displacement of the steering wheel, so how much you turn left or turn right. And the third one is the accelerometer, which is going to measure the acceleration in 3 different dimensions: x, y, and z axis. So all this data is being simultaneously fed into the auxiliary controller. And basically, the auxiliary controller is going to package all that data in a neat, organized way in order to send that as one packet to the main controller. And now I'll hand it off to Giacomo.
Yeah. So after we're getting the data from what Alex just talked about, from the auxiliary controller to the main controller, that's where we start processing the data. So that's where our whole model of the car is in the main controller. And basically, we're getting the inputs, and from those inputs, we're calculating what the outputs would be on the car. This also includes the fail-safe mechanism for if there's an error anywhere, like if there's too much power going into the system or we're not getting the numbers we're expecting, everything will shut down and keep the driver safe. But the main controller outputs 2 signals, the left motor control and the right motor control, which determine how much power that you'll give to the left rear wheel as opposed to the right rear wheel.
So to develop the control algorithm that's going to the main controller, we used MathWorks Simulink to create a model of the car. And the model generated a set of values to determine how the car would respond to a set of inputs, which include the throttle, the steering angle, and the center of gravity, or the velocity at the center of gravity, and outputs like the left throttle and the right throttle at the 2 different motors. So here's what our Simulink model looks like. Essentially, based off the steering angle given from the steering wheel, we'll calculate a desired yaw rate, or how much the actual vehicle should go left or right. And then our model will determine how much that car is actually moving. And then our PI controller, or just our control algorithm, will correct the error and make sure that the actual car is going at the desired yaw rate. And as you can see, we at the bottom, the power or the motor power distribution calculation is how we determine how much power should go on each side.
So now a little bit more about particular communication systems that we implemented. So the first one here at the top is called the UART communication protocol, which stands for Universal Asynchronous Receiver Transmitter. So looking at the top left, you have 2 devices. There's a TX, which is called the transmitter, and then the RX, which is the receiver. So between 2 devices, you would just send the data from the TX to the RX, and that's how you would communicate. So this was implemented through the auxiliary and the main controller, and we chose this for really 2 main reasons. The simplicity of it is just using 2 wires, as you can tell from the picture. The fact that it's really reliable also for longer distances, up to about 6 feet, since we're putting the auxiliary main controller in 2 separate parts of the car. And even though it's limited, even though the speeds are a little bit slower, the fact that we just need to communicate it between those 2 devices is necessary, and it fits within our system design. Looking at the bottom, we also have to worry about how we're going to interface all the sensors that I mentioned earlier and how we're going to output the left and right motor controller. This is where I2C comes into play. The integrated circuit. On the left bottom corner is how it would be implemented. Very similarly, it also just needs 2 wires. It's a data serial line and a clock serial line. That simplicity is carried over, along with the fact that I2C also has immense flexibility in terms of how it interacts with multiple devices. As you can tell, we have multiple sensors going on. We have multiple controllers. And supporting that kind of high-speed communication between multiple devices is really necessary. So yeah.
So the model that Jonathan made earlier was using Simulink and MATLAB, and obviously our system is not using MATLAB and Simulink. So what we were able to do is generate C code from that Simulink model to estimate the actual vehicle's parameters, and we used that C code and had to implement it in the main controller, but we had to heavily modify it because obviously it wasn't. It didn't fit in perfectly, so we had to change a bunch of variable names, comment out certain sections of code, things like that. And this allowed us to simulate how the vehicle would respond in specific conditions. And you see in the green box over there, that's where the linear model fits in with the main controller.
All right, so what is this? We're sort of going to start getting into what this looks like in the car. There's going to be better photos later, but it starts with 2 waterproof enclosures that we purchased. So it's sort of a metal case with a clear cover, and the cover screws on, and that it's water sealed. It's pretty strong, and the electronics all are sort of packed in, kind of like a puzzle, into these 2 boxes, and one part of the project was on the left side of the screen there. Those are 3D printed parts, so they're little pieces of plastic that get printed with screw holes pre-made in them, and the electronics screw in. And sort of why we did this is so that our customer requires that we can withstand greater than 2 Gs of force in any direction being applied to the enclosure, because as you imagine, we're in racing conditions. There's forces that we can't account for, and it's waterproof because we don't really know the conditions out there. Yeah.
And so last but not least, we get to safety. And so we took 2 different approaches to safety. We wanted to have a digital system because after all, we are making a digital product. But on the other end, we wanted to have an analog because you can't really have a glitch in an analog circuit. So starting with our digital watchdog. It is a completely separate microcontroller that's observing the behavior of the system, and if it sees something that doesn't look quite right, if it's the system reporting full throttle for 10 seconds on a very tight, windy course, that's probably not going to happen in real life, so it'll shut down the entire system. Similarly, if it sees conflicting values, anything along those lines, it can have the power to shut down the entire system completely independently of the decision-making hardware that is actually controlling the vehicle. We also have the analog safety shutdown circuit, and this is actually required by the rules of the competition that Terry Motorsport competes in. You're required to have a continuous loop or a chain, as you would, that is required to be completely activated before the powertrain of the system can even turn on. And so, as is shown on the right, it is actually just a chain of safety checks. So once you turn on the vehicle, you first make sure that all of your microcontrollers are turned on and ready to go. Then you make sure that your sensors are functioning properly, and then the vehicle gets to go ahead to get started. If anything in this chain says, okay, something's not going right, one of the microcontrollers powers down, it cuts off the entire chain. The vehicle will turn off, roll to a stop. Something that's important to note is that when we're defining safety, it's very context dependent. So we are a single car on a racetrack where no one else is going to be racing at the same time. It's a time attack event. And so this is a very different definition of safety than you would have in, let's say, a road-going vehicle where you're surrounded by traffic. And if you were to shut off the car in the middle of traffic, that is not the safest approach. But for our context, shutting down the car, giving up 1 lap time is fine. Finally, if they want to either make sure that their performance is not due to something else, or if they are concerned that the system might not be working totally correctly, you can completely bypass the entire system with the throw of a switch. And speaking of, hello? There we go. All right. Speaking of, this is what the final design actually looks like. So on the top left, you can see a top-down shot of what we developed for the project. There are actually 3 components, only one of which was required, but the rest was kind of to support and show the system working. So going from the same order we started with user input, we have a very real-life throttle and steering setup that the person can manipulate with their hands. That is feeding into our auxiliary controller, as we described before. You kind of see that roughly tracking with the diagram of the car in the top right. That sends its data to our main controller with a prominent on-off switch. And that finally goes into our mock-up vehicle, which tries to simulate the speed of the wheels, tries to simulate the behavior of the car to the best of our ability without having a $35,000 team's worth of car. To whatever end this is significant, we are very proud of what we created. It meets all of our design parameters, but Jonathan's going to talk about in a little bit what we hope to accomplish possibly in the future.
So overall, yep, our system met all the design requirements and demonstrated good performance based off our small car model. However, our model is very simple. It takes out some of the variables that an actual car might experience. So in the future, we could make a more realistic model which incorporate a lot of like aerodynamic forces and stuff like that. And unfortunately, we're not able to validate the system in an actual car because the car does not exist yet. But yes, when it does actually exist, we can actually tune like the model and everything to an actual vehicle.
And lastly, thank you to the BU College of Engineering and Terry Motorsports for helping out in this project. Thank you.
Thank you. Questions?
Thank you. This was very interesting, and this is very cool. So after you graduate, do you know who will be working on it, and what direction do you think they will take this in? Do you think they will listen to your suggestions, or do you think they might take a separate or a different route with this project?
Well, even given my position in the club, I have no say over what they do after I leave. But what we're going to do is part of the project that we didn't list into deliverables is a healthy set of documentation so that they are able to get up and running with it as soon as they need to. It is solely in their hands what they want to do with the design of it, if they even use it at all, but we wanted to make it as painless of a tool to integrate as possible.
Yeah, super cool project in this context, but I, of course, am thinking about other contexts. You did talk about some of the limitations in terms of a, let's say, road vehicle, but I'm wondering whether the ways in which you've experimented with some of the safety features on this, you can imagine having an impact in terms of safety kinds of measures or other sorts of safety technology that you would introduce with further kinds of modifications and testing in cars that, let's say, non-racing car people might drive on a road?
Yeah. So I guess I could take two approaches to this question. Jonathan at the beginning was talking about some of the competing, although not really competing, solutions, commercial solutions. And torque vectoring as a concept is not brand new. And the way that it's implemented commercially is much more complex than the way we have done it here. But to your question about safety, I think the system that we've implemented is perhaps useful in the sense that you could give your user more transparency as to what your vehicle is doing, so that let's say usually torque vectoring is used in a performance scenario anyways. So if they wanted to perhaps bring their car to a track day, but of course it's a much more complex system, they could be able to tune the safety parameters. If it's starting to throttle their performance, but say, hey, I still have more in me, then they'd be able to interact with the safety system like that.
Hi, thanks for the presentation. As someone who did my Keystone project on my own, I'm so curious to hear about your experience working as a team, and within the work that you did, if you split up certain things and people were in charge of that, or if everything was worked on as a team.
Yeah, well, we didn't explicitly say it, but the slides that we presented on are the parts of the project we worked on. So fortunately, because we had such a broad spanning project, this was actually an interdisciplinary project. So we have ECEs and we have mechies. And so they were able to work on the more mechanical aspects of it. We were able to do the coding and the wiring part of it. So we were able to get a shockingly even split of work, which made it go that much faster and with that much less conflict.
So cool, thank you.
Great job, guys. I was just wondering, you were talking about basically when something breaks or fails that it's a shutdown. Could you describe the shutdown? How quickly is this happening? And you don't know, the car obviously doesn't know where on the track you are. So could shutting down immediately cause it'd be of concern or safety concern?
That's a good question. I probably should have qualified shutdown. So in the car, there's three main systems you would interact with. You've got the go pedal, stop pedal, and the steering. So when we're shutting it down, it happens in a matter of probably 1/10 of a second. And all that happens is it stops delivering power to the rear wheels. You still have full control over the brakes because those are a completely, I guess you call it analog system. It's just a brake pedal that goes straight to the brake calipers. And steering is, again, completely controlled by you. One good point, and something that we probably should have integrated, is instead of immediately shutting it down, ramping it down. Because let's say that you're hard into a turn and you suddenly stop applying power to the wheels, that could cause the back of it to spin out. And that is a loss of control, which could be hazardous to the driver.
Can you guys talk a little bit more about Terrier Motorsport in general and what these races exactly look like?
Yeah, I can give you an opportunity to talk if it's not just me, but if you're fine. So Terrier Motorsport, they are developing, as you said, an electric race vehicle, and actually in 3 days we are going up to New Hampshire to compete against a bunch of other colleges who develop a very similar vehicle. I can go into like the whole mission statement of it, but it's basically to give young aspiring engineers a way to put what they learn in the classroom into practice on essentially, a real hard challenge. And so, as opposed to a couple of other organizations that are very focused on getting the best lap times possible at the expense of monetary expense, but also experience, Terrier Motorsport is very steadfast in making sure people have that hands-on experience, teaching everyone everything they need to know, no experience required. Sorry, I just slipped into my splash sales pitch. But yeah, it's about a 2-year design cycle for every vehicle, aspirationally.
And also, in terms of the actual competition, it's not actually like a race. It's just like a track that you drive around, and then they time you basically, and the fastest time wins.
Yeah.
Do the other universities that you race with have a similar torque vectoring system?
Yeah, they
And
do.
I don't know how often you communicate with them or with the other teams there, but I don't know.
So I guess the last year is when the last time I benchmarked everyone else. There's varying degrees of complexity to it. So some teams have 2 independent rear motors. Some teams have 4 motors, 1 for each wheel. For example, Carnegie Mellon has a very complex, very high-performance vehicle that is, a moonshot. But yeah, they do, and they have varying degrees of complexity. Some of them have a very linear model where it just, depending on the angle, that's how much power you send. We were trying to go one step above that and making it sort of an educated model that knows what the vehicle is going to be doing.
You said that right now all the parts are 3D printed. Is that what you said?
Go ahead, yeah.
In terms of, like, if you think about everything that's a physical device that's part of our project, I would say that 80% of it came from, like, the internet, or, like, it was delivered to us. So, like, the electronic components, the boxes, the wires, none of that we built. The 3D printed components are sort of, you like take a circuit board and we screw it physically to the 3D print, and the 3D print is glued to the bottom of the box. Does that make sense?
Yeah, that makes sense.
Okay.
So is there like a more official version that might be like better or more durable, or would this work in like even for like a professional grade racing race?
Okay, so if you were like Ferrari F1 coming to us.
Yeah,
I'm sorry.
essentially.
So if you were trying to do really high performance, some of the steps you could take apart from making the algorithm more advanced would be making it more of an integrated system. So currently we have wires running in between each of the boards. But if we had a larger budget and a lot more time, we would make it all one solid board. And that reduces failure points, it reduces overall manufacturing complexity because you don't have to have someone sitting there with a soldering iron. But of course, you need to make sure that you know from the get-go, this is the design I want to go with. And when we're, making mistakes and learning along the way, that would have been a big cost in terms of times and money.
Okay.
Thank you.